Let's get started. Today we'll open a new chapter, literally. This is going to be chapter 4 in your book. And it's going to be about shortest paths. So we have a whole chapter dedicated to shortest paths. So if you just look at an example of a graph, let's say something like this, then the shortest path between any two nodes, let's say this one and this one, is the number of edges on the shortest path from one to the other. So here there's a path of length, for example, 1, 2, 3, 4. But there's also a path of length 1, 2, 3. So the shortest path between these two nodes is 3. It's a very intuitive notion, and we'll use the notation that D, big D, between a vertex S and a vertex U is the length of shortest path, SP, from S to U. This is sometimes called the distance. Okay. And SP I'm going to use to abbreviate shortest path in this lecture. We also sometimes write DU when S is obvious. Like if we're only talking, if it's clear which S we're talking about, we'll leave it out and we'll just say DU. Okay, so let's take another example from the book. This one. So yeah, in here, we might ask about the shortest path between S and D. So from S to D, the shortest path length is 1. From S to B, the shortest path length is 2. In general, the problem we're going to look at is called the single source shortest path problem. This is given an input vertex S, return an array called dist, such that dist contains the shortest distances. Yeah. 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 So here, the running the single source shortest path, solving the single source shortest path problem on this graph here would return the following, would return 0 for the initial vertex because the distance from a vertex to itself is 0, just by convention. The shortest path to A is 1, to B is 2, to C is 1, to D is 1, and to E is 1. All clear? Any questions? Yeah. This one? Okay, so good. So this is the problem that we're going to solve. So there's a graph and we're given an input vertex. We're given an input vertex S. 1 second. So S, so this will be S. Okay, we're given an input vertex S. We want to return an array called dist, such that dist U, so this is for all vertices U, the dist, the value of the array at a vertex, is equal to the shortest path from S to that vertex. Right, and this is the example that I did here. So the shortest path from S to A is 1. So the dist value is 1. Okay. Thanks for the question. The questions? Now, where first about the problem definition. So you might ask, why do we formulate the question this way? Why not just say, given a vertex X and Y, what is the shortest path between X and Y? Why do we state this in this way of where we have one source vertex and we need to find the distance to everything else in the graph? Why not just give a pair? So the answer to that is that it turns out solving the problem of just X and Y, distance between X and Y, is approximately as hard as solving this problem. Put another way, if you give me a specific Q, if you say, I want to know the distance from S to D, specifically D, I don't care about the other vertices, that actually doesn't make my life much easier as a program developer. The algorithms for solving that specific question of S to D usually end up solving the whole single source problem. They end up solving from S to all the other vertices as well. Sort of outside the scope of this class to really get into why, but that's how it is. Yeah. Yes. So for each value of the array, like for this C, this is the distance from S to that C. You could also formulate another problem, different problem, which is called the all pairs shortest path problem. Here, you're asked to compute the distances between any two pairs of vertices. So in this version, in that version of the problem, your dist would actually be, this array you build would actually be two-dimensional. That's a harder problem. That's also an interesting algorithmic problem with different solutions. But there's so much research on shortest path problems that we're only going to cover some classical algorithms for this specific variant of it. Yeah. We're going to use the adjacency list data structures. Usually for this type of stuff, adjacency list is better. Now, what about, where do these graphs, where do these problems come up in real life? I can give you guys two examples, like classic examples that you will be probably familiar with. Yeah. Yeah, one is exactly this, navigation, like Google Maps or whatever. You really are looking for shortest paths, where paths are the roads or some route between locations. Have you guys heard of Dijkstra's algorithm? Some of you have. How many of you have taken a networking class? Okay, so Dijkstra's is a shortest path algorithm. We'll cover it in this class, and it's used by routing algorithms on the internet to get a packet from point A to point B. So in routing, you're also trying to find the best path, where best is going to be shortest path, but not necessarily there. It's not geographical distance necessarily. It might be things like a connection between a router has a certain capacity or a certain throughput or a certain delays and so on. So it's not necessarily related to the physical length between the routers. Anyway, that's just the application of shortest paths in the real world. We're going to be looking at different variations of this problem. Notice that in the definition of the problem, I didn't specify exactly what I wasn't very precise about the graph G. So depending on the graph G, if we can assume something about it, we can have different algorithms. The most basic version is that when the graph has no edge lengths. In other words, it's just the type of undirected graph that we've looked at so far. And that's the example here. This will cover today an algorithm called breadth first search, or BFS, for this type of graph. Then there are graphs. A graph has arbitrary edge length, or weights sometimes. So these are called weighted graphs. And their shortest paths are not just the number of edges, but the sum of the lengths of those edges. We'll cover those. And for those, it's a harder problem than the case with no edge lengths. And we need a different algorithm. And there, the algorithm will be called Bellman-Ford. Third category is graph, which is a DAG. Graph is a DAG. We've seen already, or I've told you guys many times, that when a directed graph doesn't have any cycles, it makes some problems easier to solve. And this is a great example of that. We'll see an example of solving shortest path on a directed acyclic graph. And finally, and there you can have arbitrary edge lengths as well. If we can constrain that the edge lengths are positive, this makes the problem a little bit easier than the general case. So graph has positive edge lengths. In this case, we'll see an algorithm called Dijkstra's, which some of you have seen, some of you have not, but I won't assume you've seen it. We'll see Dijkstra's algorithm to solve that case. Any questions about this so far? Yeah. It doesn't have a name, so the algorithm for the DAG, it doesn't have a name, so yeah. The graph has arbitrary edge lengths. Yep. Other questions? Okay, so let's start with breadth first search, or BFS algorithm. Okay, some of you, how many of you have seen BFS before in some other form? So some of it, you have seen it in other classes. BFS in general, these algorithms build on this idea called the optimal substructure property of shortest paths. And the idea is this. So if I have a shortest path from S, what did I say? No, from U to W. I have a shortest path from U, W. And it goes through some vertex V. This is the shortest path. I've got some shortest path from U to W. It goes through vertex V. Then this subpath from U to V is also a shortest path from U to V. The reason is if it wasn't, then we could put in whatever is shorter. If there's some shorter way to get from U to V, that would give us a shorter way to get from U to W. So let me write this formally. If the shortest path from U to W goes through V, then the part from U to V is the shortest path from U to V. And I'm not going to write out a formal proof of this. It's quite straightforward based on the intuition that I described here. Intuition mostly clear. Yeah. Any questions about why this is true? The idea is if it's actually more general than what I have written here. If you've got a shortest path, then any subpath on it has to also be the shortest path between those two vertices. It's not just from U to V, it's in fact anything. It has to be, because you could always, if there was some kind of way, like a shorter way to get from here to like here, let's say it only went through one vertex, then I could get a new path. I could get an even shorter path from U to W. That's why a shortest path has to contain within it only shortest paths. This gives us now some kind of intuition for how to construct the distances, find the distances in the graph. The idea is to go out from the source vertex from S, to go out and find everything at a distance 1. Then from there, go out and find everything from a distance 2, and expand, building up that you have a shortest path up to a certain point, so you can build out from it. Let's look at an example. Let's look at this example here. Here, we say, well, I know the distances to S is 0. And for the moment, let's just say for the other dist values, I'm going to put infinity as a kind of upper bound. I don't know what it is yet. It's less than infinity. So that's what we can start with. And then I can say, look, I'm going from S. I know everything at a distance that has the shortest path of length 1 I know that's just an edge from S to that vertex. Like E is the shortest path of length, sorry, the shortest path from S to E has length 1. That means, it has to mean there's just an edge from S to E. So I can look out along all these edges and say, well, along those edges, everything there has a distance 1. And then let's say I've got another vertex like this or another vertex like this. Let's call this D, F, and let's call this G. After I found my vertices at distance 1, I can say, well, let's look at the neighbors of that. So if something is at distance 2 from me, then it has to go, the path of distance 2, of length 2, has to go through a path of length 1. So that means I can look at all the guys for which I have distance 1. I can look at their neighbors. And those neighbors are going to be the things that I can reach at distance 2. So in this case, the neighbors are going to be G and B. The internal neighbors that are already, like here, I've already found those distances. So I don't have to pay attention to those internal edges that go back to things I've already set the distance for. I only am looking at edges going out of what I've seen so far. Finally here, I would see, okay, I've got my everything, just these two vertices at a distance 2. I look at all the edges going out of there to things I haven't yet set a distance for. And there's one edge going to F. So I can set the distance on F to be 3. That's the intuition for how breadth-first search is going to work. Now, before we get to writing it down, we need to recall the definition of a queue. So queue is a first in, first out data structure. So it stores a bunch of elements. I can inject elements into the queue, and I can eject elements from the queue. Sometimes this is called, I can in-queue or on-queue. No, I think it's in-queue elements and then dequeue elements. The dequeue or the eject works to, it returns from the queue the oldest element in there. The oldest one. That's the main difference between a queue and a stack. If you recall, a stack will return the most recent addition to the set. A queue returns the oldest thing in there. There are two operations. One is called inject, or sometimes called dequeue, also known as in-queue. I forgot what your book calls it, but these are both used. And the other one is eject, also known as dequeue. And we can assume that these are constant time operations. You can implement them using, you can implement a queue in several ways, but it doesn't matter for now. We just assume that you have these operations in constant time. So for example, if I have, let's say I have Q is X, I can, in Q, into Q, I can put Y, then Q is YX, and then I could DQ or eject Q, that returns X, because that's the old element, and Q is now just Y. Any questions on the Q before we move on? It's going to be important for BFS. So if you have any questions about how Q works or what I've written there. Okay. All right, so let's write the BFS algorithm. It takes as input a graph G and a starting vertex S. The goal of this algorithm is to build the dist vector, remember? And what we're going to do with the dist vector is initialize everything to infinity, and only when we know for sure a distance, we'll update the dist vector. So for all vertices, vertices U, we set dist U equal to infinity. And after that, we set dist S to be 0. Because this is the one thing we know, and that's going to be our starting point. We're going to make a Q with just the element S. Now, let me go back to this example. So what did we do? We, for a element like this, we looked at all its neighbors. Okay. And then those neighbors, we then looked at their neighbors. Right. And then these neighbors, we looked at their neighbors. This behavior, we're going to implement using a Q. Q is going to represent all the outer fringe, all those elements whose neighbors we have to explore next. So initially, it's just going to be S. That's going to be our starting point. Then while the Q is not empty, we're going to take the oldest element from the Q. So we're going to say U is equal to eject Q. Initially, this is always going to be S. But in general, it's going to be the oldest element on the Q. So what did we do for S? We then looked at all its neighbors, and we're going to do that now in the code for all edges from U to V. Now, we're going to look at V, like for example, we're going to look from S to D. We're going to check first, is D's dist value, is it infinity? Because if it's not, then we're going to leave it alone. But if it is, then we're going to do stuff. So if dist V is equal to infinity, then, and what we're going to do is first update its dist value. So we're going to set dist V to be what? Well, it's going to be whatever the distance was to U plus 1. More generally, we'll be like, let's say we're looking at neighbors of B. So we'll set the distance to F to be whatever it was for B plus 1. Second thing we do is we put it onto the queue. Eject D onto the queue. So then we'll be able to, at some later point, look at its neighbors. We don't look at its neighbors right away, but we put it there so later at some point when we get to it, we'll look at its neighbors. And that's it. So we're gonna, we're done with the vertex V. Then we go through all such neighbors of U. We wrap them up. And then we go back to our queue. And as long as there are things on the queue, we keep on removing them and looking at the neighbors. Finally, we'll return the dist array. Questions so far, and we'll do an example here in a second. And let's do an example. We'll still have the same example, but without the extra vertices. So initially, this is 0. Everything else is infinity. Initially, Q is equal to S. So what's the first thing we do? We pop, while Q is not empty, we eject. We set Q to be now empty and U to be equal to S. Right? And then we look at all the neighbors of S. Let's do it in alphabetical order as we're used to doing. First, we look at A. So here V is A. And the distance to A is infinity. So we are now going to go and update the distance to A to be 0, which is the distance to U, plus 1. And we're going to inject A onto the Q. Okay. Then we're going to go to another edge from S, which is to C. We're going to check if the dist of C is infinity, and it is. We're going to then set its distance to be the distance to S, which is 0 plus 1. This becomes 1. And then we inject C onto the Q. We put C there. Keep on going. So the neighbor of S is A, C, and then D. Dist of D is infinity. So we replace it with 1, and we add it to the Q. Same thing for the edge S to E. Update dist E to be 1. And we set Q to add E to it. Some space here in D, C, A. And the next is E, B, C, A. And that finishes this iteration where we had ejected S and looked at all its neighbors. We're left with this Q. Notice that this Q, the oldest guys on there, have distance 1. And right now, all of them have distance 1. So next step, we eject another element from the Q. So here we put u equals to A, and Q now shrinks, becomes E, D, C. So we look at all the edges from A. The edge to S, notice that S has a dist value of 0. So it's not infinity. It has already been set, so we don't mess with it. When we go to B, yes, B is still infinity. So dist B is infinity. So we're going to update its dist value to be whatever the distance was to A plus 1. We're going to update this to be 2. And we're going to add B to the Q. So our Q becomes B, E, D, C. If you notice our Q, it has things C, D, E. These are things with distance 1, C, D, E, distance 1. So the oldest elements have distance 1. And now we've added a new element, which is distance 2. This is where it's important that we eject always from the back, because that way we'll finish with the distance 1 vertices before we go to distance 2 vertices. That's why it's important here to have a queue and not a stack. So A, we looked at S, we looked at B, so we're done with A. We go to the next element in the queue and eject that. So we said U equals to C, and then Q is B, E, D. And notice C now has both neighbors already with a non-infinity value of this. We have nothing really to do there. We go on with our Q. We do another eject, this time D. It's the same story. All its neighbors already have a dist set. So we finish the loop and go take E. E, it's the same story. All its neighbors are set. And it's going to be the same story with when we eject B. And then we just eject everything. There's no more nodes that are neighbors that haven't had this set, and we're then done with, we have an empty queue. And then we're done with the algorithm. This is kind of like when I gave you the intuition when I started, I made the algorithm seem like it's going in these rounds that like first we do everything at distance 1, then we do everything at distance 2, then distance 3, and so on. The actual BFS, it's more continuous, so it does things one vertex at a time. But what it does is that it first does all the vertices one by one, but it finishes all the things at distance 1 before it gets to vertex in distance 2. Right? We saw that before we rejected B, we had to eject all the rest of distance 1 vertices. And it's generally the same. We have to then do all the one by one distance 2 vertices, then 3, and so on. So it doesn't quite work in these round like batches. It does one by one, but the order actually is the same as if you would do them in these round by round batches. Any questions? Yeah. I didn't quite. So what you have, these numbers that you have at the end of the algorithm, this is the distance from S. Like here, this is the distance from S to B, which is the same as saying this is the length of the shortest path from S to B. Yes, we're looking for the length, not the path itself. Absolutely. Yeah, we're looking for this value, so the length of the shortest path. It's actually, we don't go through it, but it's not hard to modify this algorithm to return the path itself as well. In fact, when you make this, when you write something like this down, you could also just write down that the shortest path to V will go through U. You can keep track of this information to recover the actual path. But we don't go into those details. Yeah. Yeah. So the input in this case is just one vertex S, and the return value is an array which tells you for every vertex in the graph the distance from S to that vertex. So it's more general. So if you want to know the distance from S to D, specifically D, you don't care about anything else. S to D. You would just run this algorithm with S, and in the end, you would look at the dist value at D. Now we'll give you the distance from S to D. The dist array, so we're building it in here. We initialize it to be infinity at all values, and then we update the array throughout the algorithm. Yeah. So you could say here, you could imagine there's a line that says dist is going to be an empty array on of size n. Yeah. The queue is this. The queue is a list of vertices like this, which we have injected into the queue. And U is this element that we eject from the queue at every while iteration. So, I mean, that's where you have to run the whole algorithm. So if you want shortest path from S to A, it's not about what is a single value of Q or a single value of U, it's about the whole algorithm. So the whole algorithm will expand, will progressively find everything first at distance 1, then at distance 2, and so on. These are not, this is not a shortest path. Maybe that's the point of confusion. The queue does not contain things on the shortest path. The queue just contains vertices that are on the fringe of things that we've explored, or the things that whose we've just said their distance vectors, but we haven't looked at their neighbors yet. It's kind of, it's a state of the algorithm. Yeah. So it's important that we look at all the neighbors of 1, things with distance 1, before we look at all the neighbors of things with distance 2. Take, for example, let's say there's this node, right? So if I am at this state, okay, so I've just explored from S. So not explore. I've ejected S and I've looked at all of its neighbors. Okay. And next and I've pushed those neighbors onto the queue. Right. So I have E, D, C, A in the queue, and now I'm ejecting A. And I ejected A. I put B onto the queue after that. So I'm at this stage. Now at this stage, I claim that it's really imperative that I eject C before I eject B. The reason is if I eject B, then I'm going to look at this neighbor of B. I'm going to say, okay, that this is still infinity. So it's going to be 2 plus 1, it's going to be 3. That's going to be wrong because really the shortest path was of length 2. It's really important that I look at C first. I look at, I exploit everything from distance 1 that I can. All right, so I will look at this, I'll find this guy and I'll say distance 2. And only when I've exploited that, then I can move on to B or to other points with distance 2. Other questions? Okay. What about the runtime of this algorithm? So let's go step by step. This is a for loop over all the vertices. This is theta n. This is all O of 1. Just this is O of 1. All of this is O of 1. How many times now is this while loop executed? Yeah. Number of vertices. So and why? And why couldn't we? So the answer is, yeah, each time we reach while iteration, we inject some vertices and later everything we inject, we eject. But is it possible that we inject something again, that we inject something ejected and then injected a second time? Why not? Because of the if condition that we have. Because initially everything is infinity, but once we inject it, we change, it's no longer infinity. And then we'll never pass this check again. We'll never add it again. Great. Execute it n times. Now, the most tricky part is this. How many times is this for loop executed? Here, yeah. M times what? M. Exactly. Okay, so just to break that down, we're going to look at over all the while loop iterations. Like, so not for each while loop iteration, how many times is this for loop executed, but look at over all the while loop iterations, how many times is this for loop executed? Well, take an edge, u to v. How many times will it be included in the for loop? Well, once when u is ejected, u to v, and another time, because it's an undirected graph, so you have symmetry, when v is ejected, and then this is the other way around. Every edge is iterated twice. So for all the while loop iterations, this loop is executed OM times. I meant in the for loop, in this for loop, every edge is, what's a better way of saying it? Appears twice in here. Yeah. The symbol next to where? U equals to eject Q. Oh, O of 1. O of 1, yeah. Yeah, so going back to their question, what I mean every edge iterated twice in the for loop means that like for every for loop, we have, for every iteration, it's for some UV. Every iteration corresponds to some UV. So there are two iterations corresponding to a single edge. Let me put that, every edge corresponds, every edge corresponds to two iterations of the for loop. Only one of those times does it change its distance value. Yes. So now this gives us the running time. Well, we have the initialization order n time. This eject is executed on time as well. And this for loop is executed, as we said, O of m times, and inside is just constant operation. So the total time spent in this for loop over the course of the algorithm is order m. This gives us order n plus m time. And this is fast. We already talked about how if you're even going to read the input, you need this much time. Like the adjacency list takes this much space, n plus m space. So even reading it, you're going to use this time. So this is a fast algorithm, as fast as you can get, really. It also gives something called a BFS tree, which is similar to a DFS tree in the sense of it captures how we are, which edges we're exploring. So we start from S, and from S, remember, we went to A, or at least we analyzed the edge from S to A, then we analyzed the edge from S to C, then from S to D, and then from S to E. And then later we analyzed from A to B. We have this concept of a BFS tree, which is, by the way, different from the DFS tree. You can compare it here. So what is DFS going to do here? It starts with A, S, but then it goes down. So it's like that's where the depth first comes from. We go from S, we go to A, we go to B, and we go to C. A, B, C. Right? So we go from S to A to B to C. Then we stop and we back up and we go D to E. So these trees are look very different. The DFS tree is great for answering questions about connectivity. Like it tells us whether there are paths between two nodes. The DFS tree preserves that information about paths. But it's not good for capturing anything about distances. Like the distance from S to C, if you were to look in this tree, it would be 3 nodes. Like that's what DFS, the path that DFS found. It's 3, edges. But that's not the shortest path. The way the BFS search is done, the S to C here is the shortest path from S to C. Questions? All right, let's change gears a little bit to go to now this weighted graph version of the problem. So a graph is weighted if every edge E has an associated, and every edge E from U to V has an associated integer LE, referring to the length of E, also known as LUV, also known as LUV, like this. So we may be using, or the book may be using all kinds of variants of this notation. This all means just the length from U to V. Okay, this is length, also called weight. We sometimes refer to this as weights or sometimes lengths. It's all the same thing. Okay. In fact, most graphs in real life are going to be weighted. So for as we talked about navigation, the distance between 2 cities, there's the actual length. Or for routing, there may be a throughput or something like that between any 2 routers. So this is pretty common in practice. And in this graph, the length of a pass is it's no longer just the sum, the number of edges in the path. It's the sum of the lengths of the edges in the path. So for example, here's a graph S going to A, going to B. And let's give it some weights, 100, 50, and 200. Here, the shortest path from S to A is 100. The shortest path from S to B is 150. This is the important distinction, that it's not, this 200 is not the shortest path. Even though it has one edge, but this guy has two edges, it doesn't matter. We're not counting anymore the number of edges, we're counting the total sum of weights. So why not run BFS to solve this problem? Well, BFS no longer works. And this graph is an example. What is BFS going to do here? Going to start with S. It's going to say, all right, I got two neighbors, A and B, and the distance to A is 100, and the distance to B is 200. I'm done. Goodbye. See you later. Whole point of BFS, it's predicated on expanding according to the number of edges. First one edge out from S, then two edges out from S. So it's really going in that order. And so if the shortest path actually uses more than the minimum number of edges, like in this case, BFS is not going to work. Now you might have negative weights, and that's totally fine. For example, you can have S, 3 to A, 4 to B, and -2 to B. In some applications, this may not make sense, but in others it might. So for example, if this represents either some penalty or some profit from using a certain route, then you can have positive values represent like the penalty you pay. You want to minimize those, but the negative values are actually profits for you. So in this graph, what would be the length of the shortest path from S to B? Yeah, it'd be 1 because you would do this guy. What about from S to A? What would be the shortest path length? 2, because you could go like this. So no problem with that. However, there is a problem with something called negative cycles. So we will assume there are no negative cycles, because otherwise shortest path is not well defined. I'll explain why in a second. So if I add here like a -1 and a 1, I've created a negative cycle. I've created here the weight of this cycle is -2. So what's the shortest distance from S to A? You could go like this. This gives you a distance of 2. But if you take this cycle, now you get 2 minus 1 plus 1 minus 2. You get a new distance of 0. If I take this cycle again, I get a distance of -2. And I can keep on taking this cycle till and I'm always going to decrease my weight. So shortest paths don't make sense if there's a negative cycle, because then the minimum is not well defined. Yeah.
Like, for example,
Yeah. S. Yeah.
Or is that not allowed?
You can. It's allowed. But if you want to make your life easier, add a node here, T. So here, S to T, you could go in here as much times as you want to get a shorter path to T.
Yeah, I was target node.
Yes, yes. But that's exactly the logic, which means that shortest path no longer makes any sense, because why that doesn't make any sense. And if your shortest path goes to a node, to your destination, and keeps on going and becomes shorter. Other questions? Okay, now our algorithm is going to be very, very simple. It's going to apply, it's going to start with the same way as BFS, meaning it's going to set this dist vector to infinity for everything except S. And then all it's going to do is going to be a bunch of these update operations. Update UV is going to set dist V to be the minimum of 2 values. First, whatever it was before. So we're going to try to make it better, but we'll never make it worse. And the value we will try to make it better with is dist U plus the length of the edge from U to V. In other words, if I have like S here, I have some path to U of length 5. And I have an edge. I have S, path to U of length 5, and I have an edge to V of length 2. So let's say I've computed dist U to be 5, and let's say V is 6. So in this case, I check dist to U plus LV, 5 plus 2. It's more than 7. Sorry, it's 7, so it's more than 6. So update does not change. They does not change dist V. But if dist V is 9, then update sets dist V to be 7. Yeah. No, we're not running BFS. We're just going to do a bunch of updates in a very specific order till we're blue in the face. All right, that will be the idea. Okay, but all we're going to do is do these updates. Now, the intuition behind these updates is that our dist is going to be an upper bound on the true distance. This is called the upper bound lemma. The upper bound lemma states that if we start with dist s equals to 0 and infinity for everything else, and then do any sequence of update operations, then the true value, the true distance to u is upper bounded by our value in the vector for all u in V. You can now think about this, what this update operation is doing is it's saying, look, we have some kind of value which is an upper bound on the distance to u, and we can get to V via this distance to u or less, and then this edge 2 of length 2. So that means that there's a path to V that's upper bounded by 5 plus 2. That means that the path, there is a path from U to V that's at most 7. So the shortest path to V is 7. Maybe there's something way better, but it's got to be 7 or less. And if that gives us something better than the upper bound we have, then we update it. If not, then we leave it alone. The proof is by induction on the number of update operations. So base case, it's going to be trivial. So we haven't done any operations. We've said dist s to 0 and everything else infinity. And trivially, that's an upper bound on the actual shortest path. Infinity is bigger than any other number in this logic. So for the general case, we have two possibilities. So we've got remember, we've got this S, path to U, edge to V. So two possibilities, one that we update, another one that we change dist V, another one is that we don't change dist V. So if we don't change dist V, so that means that the bound that we had already is less than or equal to the new bound we might potentially have. Okay. Then dist V does not change. And so it doesn't change. So it was good enough before, and it's good enough like before this, it satisfied the induction hypothesis, and now it still does. So induction hypothesis is still satisfied. I'm going to need to run about 1 or 2 minutes over time to finish this, just to keep you guys in the same place as the other lecture. But we're almost done here. Yeah. It's going to take more words to write out than just to say. So I'll just say it again. In the base case, before you do any updates, so this is I'll write this. This is before any updates. You have that dist s is 0, and this everything else is infinity. And we need to say that this is upper bound for the true distances. True distance to s is actually 0, so dist is trivially an upper bound. And the true distance to everything else is some number, and infinity is always an upper bound for any number. So, sure. Now going back to the general case, the other situation, the more interesting one, is if we are going to make a change. So dist v is more, the previous bound is more than dist u plus LUV. Okay. So then what do we have? We have the true distance to v is upper bounded by the true distance to u plus LUV. This has nothing to do with the algorithm. This just is because you have this path. So the shortest path to v, it's smaller or equal to than the length of any path to v. And one of the paths to v is this one that goes through u. And that one has this distance. So the true distance to v is either given by that path or something less. So that's where we get this. Now here we can apply the induction hypothesis that du is upper bounded by dist u plus LUV. And this is in fact, this is the new value of dist v after the update. In other words, the new value after the update is an upper bound on the true distance to v. That's the end of the proof. Any questions? You can all, yeah, if you have questions, stop by afterwards, because I guess people want to go.